Okay, this is Unit 3, Day 5a, and we're going to do some solving of exponential and logarithmic equations. And the key to today is remembering that they are inverses of each other. So an exponential is an inverse of a logarithm, and a logarithm is an inverse of an exponential, and they can undo each other. So anytime we want to get rid of one, we're going to use the other to do it. Okay, so first off, solving exponential equations. An exponential equation is one in the form b to the x equals a, where the exponent includes a variable. So recall, to go from exponential form to a log, you go to this way. That's the way it's written here. We can use this along with change of base formula to solve exponential equations. Now the first guy here, number one, we got an exponential right here. And the problem is I can't isolate x until I isolate 2 to the x. I have to isolate all of this, and then I can worry about getting x by itself. So we'll work on getting this part that I circled by itself first. So I'm going to add 50 over. So if I add 50, I get 3 times 2 to the x equals 293. Again, I'm going to divide by 3. Get that 3 out of there, so 2 to the x is going to equal, and I'll just leave this as 293 over 3 for right now. And now to get rid of that base of 2 with this exponential, I'm going to use a logarithm with the same base. So I'm going to take the log base 2 of both sides. So now log base 2 of, and this is my argument, and this is my argument. Now on the left side, when it says 2, this is saying 2 to what power equals 2 to the x. So 2 to what power equals 2 to the x? Well, that'd be x. So I can replace all of this with x. And that just got x by itself. Now on the right side, type that in the calculator, change the base. You do the log of 293 over 3 divided by the log of 2, the common log, or you do natural logs too if you want. But you get 6.61 when you put it in the calculator. Get this guy over here. And here's the exponent, there's the base with the exponent. So I need to get that by itself first. So I'm going to divide both sides by 20, so it'd be 1/2 to the t over 3 is going to equal 1/4. Should have pushed that over a little bit. Let me rewrite this. Put it over here, leave a space. Because now I'm going to get rid of this base of 1/2, I'm going to use log base 1/2. So on the left side here, 1/2 to the what power equals 1/2 to the t over 3 would be t over 3. So this really just wipes it out, cancels it out. On the right side, 1/2 to the what power equals 1/4. Well, that'd be 2. You can put it in the calculator if you want, but just save some time. If you take 1/2 squared, you get 1/4, so it's squared, it's 2. Then multiply the 3 over, so t equals 6. Number 3, again, look at what is actually being taken to a power here. It's the base e is being taken to the e to the x, or I'm sorry, negative x power. So I need to get rid of the 3 and the 2, so I'm going to subtract 3. So 2e to the negative x equals 3, divided by 2, divided by 2. Okay, it was brought to my attention that the audio went out on this problem. So I'm just going to start from here. I think it was somewhere in this problem where the audio went out. So I'll just explain how things were going here. So first off, divided both sides by 2 on this one. I got e to the negative x equals 3/2. To get rid of that e, I use a natural log, because to get rid of a base of e, you use a log with a base of e, and natural log is that log that has a base of e. So I natural log the left side, natural log the right side. On this one, this would be a negative x would equal a positive 0.45. And then as to switch the signs, you get a negative 0.405. Over here, first off, multiply both sides by 3. So that's how I got the 12. You guys got the 12 here. So on this step, kind of a trick here, I'd love to combine these together. I really can't. But I'm going to try to get rid of that negative x up there. So I'm going to multiply everything by 2 to the x. And what that does, when I multiply by 2 to the x, this first one, when I have 2 to the x times 2 to the x, since the bases match, you add the exponents. So it would be 2 to the 2x. If I have 2 to the x times negative 2 to the negative x, well, you'd add the exponents. X plus negative x would be 0, so it'd be 2 to the 0. And then over here it'd be 12 times 2 to the x. So I multiply everything by 2 to the x. And what happens here, the 2 to the 0 is a 1. So that's going to be a 1 right here. I brought this to the left side, okay, because I want to equal 0, and then leave that one alone. And now, if you have 2 to the 2x, when you got a power to a power, I think when you do a power to a power, you multiply the powers, get 2x and the exponent. Here I'm going to split them. So I'm going to say that this was actually 2 to the x squared. I'm going to think of it that way. Okay, and then this guy here, didn't really change a lot of the rest of it. Now, if I let w equal 2 to the x, so every 2 to the x I see, just let it be w. Instead of 2 to the x squared, I'll have w squared. And instead of negative 12 times 2 to the x, I'll just have negative 12w, and then minus 1. And so when we do that, we're kind of covering up the 2 to the x part and just looking at it as a quadratic. So treat it as a quadratic. Can't factor it, so I'm just going to use quadratic formula. So plug everything into the quadratic formula. Notice you have plus and minus, but here I threw the minus out. I didn't do minus because 12 minus the square root of 148, well, the square root of 144 is 12. So this is going to be a little bit more than 12, which means I'll have a negative. If I do 12 minus, I have a negative, and I don't want to have any negatives on this one, okay? The only reason I say that is because I am looking ahead, and I have to get rid of this 2, I have to use a logarithm with the base of 2. You can't have a negative in the argument. So since I know, and hopefully you'll figure that out as you go, like, well, if I'm going to have to use a log, I can't have a negative in there, so you just throw out that negative. Now you probably, say you didn't catch it early, you would have caught it down here, like, oh, I can't do a minus. If I do log base 2 of 12 minus all of this stuff, it says error on my calculator, and you would have caught it, so it's no big deal. So I'm just going to use the positive root, so that equals w. Well, actually, I'm going to replace w with 2 to the x, so go backwards, because remember 2 to the x equals w, so w equals 2 to the x. So put 2 to the x in there, do log base 2 of both sides, so log base 2 of both sides, log base 2. On the left side is just x, and then over here it'd be 3.595. Okay. Again, apologize, all the works are hard to hear, but if we have logarithmic equations now, we're going to use bases. We're going to use exponentials with those kind of bases. Whatever base the log has, that's what kind of exponential I'm going to use. My first step is to get the logarithm by itself. Right there is the logarithm, okay? So I need to get rid of the 5 and the 4, which is what I did. So I subtracted 5 divided by 4. I got down to this right here, and that's where if I have a log with a base of 3, use an exponential with a base of 3 to get rid of it. And what this is saying is, this logarithm says 3 to what power equals 3x minus 1? Whatever that magical number is, now I'll take 3 to that power. So what is it going to equal? 3x minus 1. So it's just kind of nice how that works out. That really just, you're not actually canceling, but this part right here basically goes away and just the argument is left. On the right side, 3 to the 4th is 81, and then solve it like a normal equation. Over here, I use my properties first off. So take this 2 up top here. That's an x squared. It's a minus, so I'm going to combine the arguments by dividing. So I got natural log of x squared over 3 equals 1. Now, to get rid of, again, this natural log has a base of e, so to get rid of it, I'm going to use an exponential with a base of e. So e to those powers, and on the left side, I get x squared over 3. On the right side, just e by itself. Square root, I'll multiply by 3 first, get 3e, and then square root. When you square root, you get a positive and a negative root. But, again, on this one, when I'm checking my extraneous solutions, if I plug in a negative up here, you can't have a negative in the argument because e to no power equals a negative radical 3e, so that can't work. So only positive radical 3e. Backside, more of the same idea. Here I got 2 logs. They both have a base 2, which means I can use my properties. This 2 I put up top first, so I'm condensing, put it as a 2x squared, which 2x squared is actually 4x squared if you multiply it out. division or subtraction means division. So I'm to here, when I combine those, again, to get rid of that log with a base of 2, use a base of 2 with an exponential with base of 2. So I take 2 to both sides. What's left? Now 2 to the 5th is 32, and I got x over 4x squared. I set this up as a proportion and set cross products equal, so x, 1 times x, would equal 128 x squared. And then on this one, bring the x over. Yeah, don't divide. Some people would divide by x. They want to divide by x, and I never divide by a variable. You're going to lose a variable. You actually lose a possible answer when you do that. So never divide by a variable to try to eliminate something or get it away from one side. So equals 0. I did some factoring. My two answers are 0 and 1 over 128. Again, arguments must be positive. So if I plug a 0 in there, 2 to no power equals 0. It can't happen, so you throw that one out. That's an extraneous solution. 1 over 128 does work. Same idea here. Plus means multiply, so 4x times 2x is 8x squared. I use a base of 2. So on this side I got 8x squared. 2 to the 8th is 256. And now just solve like a normal equation. Divide by 8. You get x squared equals 32. Take the square roots. You get plus minus 4 radical 2. Then you want to check, do these both work? So plug them back in up here. The positive one works, but the negative does not work. If I put the negative in here, that would be a negative 16 radical 2 for an argument. You can't. So 2 to no power equals a negative, so you have to throw that one out. Now, it's not that you always throw negatives out. There are times where negatives do work. It's what happens when you plug it in and you simplify. Does the argument stay positive? And that's what matters. Okay. So down here, I'm kind of following along here. I've got a plus, so I've foiled these two together to get x squared plus x minus 12. I put that 3 up top, so it's natural log of 8. Now get rid of the natural logs by using a base of e. And it cancels out on both sides. That's nice. Cancel on both sides. So I got x squared plus x minus 12 equals 8. Bring the 8 to the left side so it equals 0. Okay, and then this one does factor. Factor this into x plus 5, x minus 4. So my two solutions, possible solutions, are negative 5 and 4. Problem is, again, if I plug a negative 5 in here, it's not that negatives are bad here. It's that after you plug it in, is this negative? So negative 5 minus 3 is negative 8, and that's what makes it bad. Throw it out. 4 barely works. 4 minus 3 is 1, so that it's still positive. That works. Now, if this was, say, a 2, because like I said, being negative isn't always bad, and being positive isn't always good. If this was a 2, 2 minus 3 is negative, so I'd have to throw that out too. So basically, anything 3 or less has to be thrown out. Over here, let's say if it had been a negative 2, so just this is like pretending, if x was negative 2, and this was the original question, like throw this one out, act like that's not there. If I plug negative into this, that is still a positive argument, so it would be okay to use a negative there. Now, of course, if this whole equation, that doesn't work like that. We have to throw that out too. But it is possible for negatives to be good and positives to be bad. It's all about what happens after you simplify the argument. So plug back in, make sure the argument is positive. Can't be 0, can't be negative. And then these are kind of older problems with investing, compounded quarterly, compounded continuously, and that kind of stuff. If you remember, here's our kind of basic setup. So the amount with respect to time is going to equal your principal, and then it's 1 plus, and we have a 1 here because if it has to do with money, you better be making money. We don't want to be losing money if you're investing. You're pretty bad at investing if it's not a 1 there. So the 1 means you keep what you started with plus some more. And this R is your interest rate, your annual interest rate. N is the number of compounds per year. So when it says quarterly, this N is going to be 4, because 4 times a year. And then the power is going to be time in years times the number of compounds per year. So if it's compounded quarterly for 2 years, well, that's 4 times a year for 2 years. That's 8. So 2 times 4 is 8. So down here, plugging stuff in. So an investment of $2,000, that's my principal, has a rate of 5.75%. put that in as a decimal, 0.0575, compounded quarterly, so I'm dividing by 4, and then 4 times a year times the number of years. How many times do I have to do that until it's worth $3,000? Okay, so first thing I did, I'm basically just trying to solve this equation. Notice the variables in the exponent. So it's like those first few problems that we did back here, where we got variables in the exponent we want to solve for. So we're eventually going to have to use a logarithm at some point. But first, I need to get the thing that's being taken to a power by itself. Well, that thing is all of this. So I need to get rid of the 2,000 first. So I divided by 2,000. Now that leaves on the left side 3 halves. I just reduce this 3 halves. You can put 1.5 if you want. I'm just kind of being lazy. I'm not going to put it in the calculator until I have to. Equals, and now all of this is 1.014375. I want to get rid of that base of 1.014375, so I'm going to use a logarithm with that base. So log base 1.014375, and you think, I didn't know you could do that. I didn't know we could have decimal bases, but you can. And to find this, just use change of base formula on your calculator. So type this in the calculator, log, so common log or natural log of 3 halves divided by the common or natural log of 1.014375, and you get 28.4085. Over here, it's just going to be 4t, that's all that's left. And then divide by 4, so 7.102. Number 7, initial deposit of $200, so there's 200, is now worth, so my final amount right here. Now this says 8.4%, again that's 0.084 as a decimal, compounded continuously. So if it's compounded continuously, that means your base is E. That's the whole point of E, is figuring out what would be your rate if something compounded continuously, like how nature works. Nature and how bacteria grows and that kind of stuff. And think about how things decay. Things don't decay. Every 2 minutes, lose something, things just continuously decay. So it's always happening, and populations are continuously growing. The babies aren't all born on the first of the month, and then all the deaths happen on the first of the month or anything like that. It's always just kind of rapidly changing. So E takes that into account. So principal, base is E, the rate, again, which maybe I put this, so the amount with respect to time is going to be principal, E, and then the rate, and then the time. So a lot of people call that PERT, P-E-R-T, PERT, or R and T are in the exponent. So I plugged everything in, got this equation. Again, got to get the 200 out of there first. So divide by 200, I got this decimal. Put it like that. And then I took the natural log of both sides. So I want to get rid of this E here. So the natural log, get rid of that. The natural log of this big number is 0.504. On the right side, just 0.084t, and then divide and you get 6. So it took 6 years. That's a really good interest rate, by the way. It's a ridiculous interest rate. If you don't know, look up bank rates right now. They're in like the 0.1 to 0.15% range. So not even a tenth of a percent, or close to just barely a tenth of a percent. And then number 8, a certain compound has a half-life. So remember how to do half-life. Okay, so half-life is your base is 0.5, and then up here you've got t divided by whatever half-life is. This way, after 12.5 days, if I took 12.5 divided by 12.5, that's a 1. So it'd be 0.5 to the first power, 1 half-life. My principal, quote unquote, where I'm starting with is 20, and I want to end with 5. Okay, so again, the first step, always divide this over. 5 divided by 20 is 0.25. So I got 0.25 equals 0.5 to the t over 12.5. Get rid of that 0.5 with a natural log base 0.5. And this here, so half to what power equals a fourth? I did this one in my head. Half to what power equals a fourth? That's squared. So it'd be a 2. So this whole side is a 2. This side is t over 12.5. Multiply that over, it's 25 days. Okay. Sorry, this was kind of fast, but unfortunately my audio went out in the middle of recording, so that's why that's why I have all my notes done already. So hopefully that helps. I'm going to try to put these together, and if I didn't, then obviously you had 2 videos to watch today. But